The last part of the discussion on the traditional states of matter is solids, and the first thing we're going to do is address this up here. As a reminder, all this material is in chapter 10.3 in your book, Modern Chemistry, and it starts on page 577. Instead of saying that particles in a solid hold relatively fixed positions, we're going to make it nice and simple and say simply that particles hold fixed positions. We're going to assume that every atom or molecule in a substance is frozen in place. As a quick review, remember that intermolecular forces determine what state a substance is in, depending on other conditions like temperature and pressure. For liquids, the intermolecular forces are strong enough to pull the molecules or atoms together, but not strong enough to keep them frozen in place. And in gases, intermolecular forces are so weak that the individual molecules of the substance are free to roam about the container that they're in. This first bullet point makes solids seem like they have the same characteristics as liquids, except remember, the shape of a liquid depends on the container in which the liquid is contained. For solids, their shape is locked in. It doesn't matter what you throw the solid into, it will keep the shape that it has. And again, all the particles in a solid are basically frozen in place. Even though the particles are frozen in place, however, they are still moving. They're just not bouncing around the container like they would in a gas. They're not sliding past each other like they would in a liquid, but they are vibrating in place. They do have kinetic energy, and similarly to before, the higher the temperature, the more these molecules or atoms must be vibrating. And again, this all has to do with the strength of the intermolecular forces between and among all of the particles. For the purpose of distance or e-learning, we're going to basically just concentrate on these two sub-bullet points here. We're not going to worry too much about the sub-bullet points here. The term amorphous comes from Greek, and it means without form. What that means is on a molecular or particle level, a material does not have any kind of recognizable repeating structure as it would with a crystalline solid. Crystalline solids are composed of regularly repeating structures called crystal lattices. If you remember from a previous discussion, we referred to table salt or sodium chloride as a substance that occurs as a crystal. There's a regularly repeating structure of alternating sodium and chloride ions in this structure that we call salt. Just for kicks, let's add in a few of these typical examples for the remaining crystalline solids. Covalent network crystals might be something like diamond. In a diamond, every carbon atom is attached to 4 other carbon atoms, and this forms a 3-dimensional structure that's basically endless. So a single diamond is basically a single really big molecule. I know I never used to think of metals as being crystals, but they are actually in a crystal structure. If you looked at a very tiny photograph of a piece of metal, and I'm talking like submicroscopic photograph, you would see that the metal atoms arrange themselves in a regularly repeating structure. They actually form crystals. And finally, the classic example of the last one, covalent molecular crystals, would be water when it's in its solid state, in other words, ice. 9 times out of 10, solids are denser than liquids for the same material. An exception, of course, being ice, which is actually less dense than the liquid. But that's, as I mentioned, an exception. 99 times out of 100, when something freezes from the liquid form to the solid form, it becomes more dense. Because the molecules in a solid are already so very close together, it's virtually impossible to squish a solid into an even smaller volume. That's what we mean by incompressibility. And if you remember our discussion about diffusion in gases and liquids, diffusion is the motion of particles of one material through another material based on those random motions of the molecules or particles. Of course, in a solid, when all of the particles are frozen in place, it's virtually impossible for them to mix. If you put two metals together, it's not like they're going to mix into each other when they're solids. That's what we mean by low rate of diffusion.